Thank you very much. Good morning, everyone. So I'm working at the IAP in Paris, and I'm working mostly on the modeling of gamma ray burst, the prompt and afterglow emission. I'm also interested in the progenitors, the populations, the link of some gamma ray bursts with gravitation, such topics. And on the more observational side, I'm also deeply involved in the SWAM project, which I think will be presented this afternoon. So I will say much more today, this morning. So I'm supposed to give an introduction to multi-messenger astrophysics and more theoretical side. So it's quite challenging because it covers many different astrophysical sources and a lot of diversity in the evolved physics. So I will make a selection with a strong personal bias. So as you know, there are 4 messengers, so photons, on which most of astronomy is based. And then 3 other messengers. So immediately to gain time, I will skip cosmic rays, because cosmic rays, these are suprarelativistic charged particles. So it means that they are deflected by magnetic fields. So it can be in the source. This is probably how they are confined to be accelerated, but it's also along all their paths towards the Earth, which means that you can easily lose the information on the direction of the source. And in addition, for a transient source, you can also introduce a big delay between the arrival time of cosmic rays compared to light, for instance. So it makes multi-messenger astronomy with cosmic rays somehow much more difficult, or very often with quite indirect arguments. And so I will skip that. And in addition, I'm not at all an expert in cosmic rays. So I will try to say a few words about neutrinos, which, as you know, are particles which are interacting weakly with matter, which of course is both an advantage and a big challenge. It's an advantage because if you observe a distant source in neutrinos, in principle, you can assume that the signal has not been affected by the propagation. So you have a direct information, physical information on the source. But on the other hand, the challenge is the fact that not only the universe, but also the detector is transparent to neutrinos, which makes the detection difficult. Okay. And then gravitational waves that are, of course, a perturbation of space-time, which is propagating, and which we'll see carries also a lot of information, physical information. So a few words about neutrinos, because somehow we could say that the first true multi-messenger source is the sun with the observation of solar neutrinos. So as it is well known, I will try to go fast. You know that these neutrinos are produced by the fusion of hydrogen into helium in the core. And so when you change 2 protons into 2 neutrons, you produce 2 neutrinos. There is a very nice and clear prediction. So the well-known number, which is sometimes printed on the walls in labs, 60 billions of solar neutrinos per square centimeter per second on the Earth. And even more than that, there is a detailed prediction for the spectrum of solar neutrinos. And then, of course, it was really a big challenge on the experimental point of view. And one main difficulty was that the first experiment had a low energy threshold, which was much higher than the mean energy of solar neutrinos. So the comparison with the theoretical expectation was quite difficult. But with time, this low energy threshold has improved. And for instance, Borexino, more recently, has now a low energy threshold, which allows to probe more or less the whole solar spectrum. And at the end, 2 major results: an excellent agreement between the observation and the theoretical prediction. So somehow it's impressive. It validates most of what we have understood about main sequence star during the 20th century, and especially their source of energy. But in addition, you know that to have this good agreement, you need to take into account the oscillation phenomenon, which has been discovered with this method, and which somehow opens the door towards physics beyond the standard model. So it's very interesting. So there is, of course, a second very well-known source in this MEV neutrino range, a nearby core collapse supernova observed in 1987, sorry, and it was in the Large Magellanic Cloud. And here again, really a lot of information only with a single event, because somehow the number of neutrinos and their energy is fully compatible with the order of magnitude of the total energy released in the core collapse, and somehow shows that most of the energy has been emitted as neutrinos. Then the duration of the neutrino burst shows that they are originating from a very small and compact and dense source. You cannot prove directly that, for instance, it's a neutron star, but you can really show the formation of a very compact source. And finally, the delay between the neutrinos and the night, so about 3 hours, is also fully compatible with a scenario where you form first this compact source, and then you have a shock wave propagating in the envelope of the progenitor star, and you observe the first light only at the shock breakout. And in addition, on the point of view of fundamental physics, you can also use this delay to put a limit on the mass of the neutrino, which is quite interesting. Because, I mean, the travel time is about 150 kilo a year, and the difference is at most 3 hours. So more recently, of course, we have started to detect high energy neutrinos. So either in the ice, in Antarctica with ice cube, or in water in the Mediterranean Sea with Antares and now KM3net. The idea is that now the neutrino is interacting with matter in the Earth, and then you observe the Cherenkov light of all the shower following the production of muons. Here, the first sources have started to be detected in 2013. So the number of sources is still small, but on the other hand, what is interesting is that we have already quite some diversity. So it started with a background. So maybe I won't spend too much time to discuss background this morning, because somehow most of you are interested in the follow-up of transient sources. So background, I would say, is mostly for you a matter of hope, because it means that with a gain of sensitivity, there are new sources to detect, but at that stage, they are still unresolved. And then, so a first possible association between one high-energy neutrino and a flaring blazar, and more recently, maybe the first persistent source with a nearby galaxy with an active nucleus. So if it is confirmed, this figure shows that probably there is a lot of theoretical work to do, because you have a comparison of the typical prediction for from such an AGN and the current detection. So I think I will skip this part on background, but a very interesting result, a recent result, is the fact that maybe now it starts to be possible to separate a galactic component in the background. Okay, I skip that and I move to gravitational waves. So first, probably everyone knows the principle for the detection. It's based on the fact that when a gravitational wave crosses a region of space-time, it will affect distances or duration in a way which is direction dependent. So you can use an interferometer to detect such waves. And of course, the challenge is in the order of magnitude of the relative variation of distance or duration, which is called the strain, and which for typical astrophysical sources we detect today is of the order of 10 to minus 21. So we know very well this number, but we should always remember really what it means. So if you build a detector with the size of the Earth, 10,000 kilometers, so it's Monday morning, but 10,000 kilometers, it's 10 to 7 meters. So times 10 to minus 21 is 10 to minus 14, so 10 femtometers, so a big nucleus, okay. But of course, it's difficult to build an interferometer the size of the Earth. So typically with LIGO Virgo, you could consider that the distance is of the order of 100 kilometers, because the true distance is a few kilometers, but you have a Fabry-Perot cavity to increase this distance. And so you lose 2 orders of magnitude compared to my previous estimates. So it's about a fraction of protons that you want. And so this makes the challenge, and somehow you succeed to do the measurement thanks to the statistics of your high number of photons interacting with your mirrors. And this is where, for instance, the power of the laser is a key ingredient in the sensitivity of your instrument. A very interesting feature regarding the follow-up is the fact that due to the very peculiar geometry of such a detector and the properties of gravitational waves, you have some kind of antenna pattern. You have not the same sensitivity in all directions. And so this is something you can use to improve the localization in some cases, which of course is very interesting because localization is a key point in the follow-up. So, okay, you know that. So here, just to remember that I won't discuss all the source of background in such an interferometer, but of course, something which is really difficult to suppress is the seismic noise, which is giving somehow the low frequency threshold of your instrument, which means that on ground, we are limited to this hertz, kilohertz region, and that we have to go to space if we want to observe, for instance, in the millihertz. Okay, I will skip that. And this is just to give the landscape. So there is still a lot of interesting perspective because we are somewhere around this gray line on the top, maybe a little better now. And we will move in the coming years, hopefully, at least at the blue line, maybe orange. And then for the youngest among us, we may hope to reach with either Cosmic Explorer in the States or Einstein Telescope in Europe, the purple and green line in the future, which will be really a very significant improvement in terms of sensitivity. And what is very interesting, as you know, is that the quantity you measure, the strain, is varying only like 1 over the distance. So when you double or when you divide by 2 the minimum strain you can detect, you multiply the maximum distance by 2, the volume by 8. So the number of sources which are accessible is growing much faster than for photons or neutrinos with a flux like 1 over d squared. Okay, so as I told you, we need to go to space if we want to measure millihertz gravitational waves. Don't ask me how you have an interferometer working with arms of 2.5 million kilometers. I don't know. And for nanohertz, now it means that the wavelength is of the order of 10 of parsec. So the idea is to use an array of pulsars, and you make a cross-correlation between Raval times of all your network of pulsar. You use millisecond pulsar, which are the most precise clocks you have in your vicinity. And with that, you can hopefully detect gravitational waves at such low frequencies. So it leads to this famous plot where you have the typical sensitivity as a function of frequency with the sensitivity of current and future instruments. And the shaded region gives an idea of the level of predicted signal with the most promising sources. So typically, for the moment, we are limited to this technique, and we probe stellar mass binary system, and maybe a hint of detection of the background in this region. And it could be, for instance, the superimposition of all supermassive black hole merging in the universe. Okay. So it's a very bad choice of color, I'm sorry. So the idea is that the gravitational waves are produced by the accelerated motion of masses in space-time. So there is a famous formula predicting the power emitted by such a system. And what is really frightening in this formula is not the fact that you have a triple dot on top of the Q, but the fact that you have a G over C5 prefactor, because G is small and C is large. So G over C5 is really a big problem. And so here there is a trick. If you take a typical source with a mass M, the size R, you can compute the associated quadrupole, which somehow is the geometrical quantity you need to compute this quantity. So it goes like m over m times r squared, and you have a prefactor dimensionless, which is associated to the geometry, because for instance, for a sphere, the quadrupole is 0, and for a binary system, the quadrupole is much better because it's very flat. And then you can also say that the typical time scale of your system is r over v, and with that you can derivate your quadrupole and estimate your power. And at the end, you get this result where you have only dimensionless factors. So S is the geometrical factor I mentioned. Psi is a compactness parameter, so gm over RT squared. So somehow it measures how far you are from being a black hole. And beta is, of course, the velocity in unit of c. And what is really funny is that now the prefactor is c5 over g, which is now very large. And so it shows that to have a source of an astrophysical source of gravitational waves, you need to fulfill simultaneously three very strict conditions. You must be as far as possible from spherical symmetry, IS. You must be as compact as possible. So that's why we speak of neutron star and black holes, IXI. And you need to have a velocity which is close to the speed of light. That's why typically we detect system at the very end before the merger when the orbital motion is relativistic. So for instance, obviously, a merger of compact objects are excellent sources because they fulfill all six conditions. We often discuss the possibility in the future to detect core collapse supernovae, but it's much more difficult for a clear reason. I mean, condition 2 and condition 3 are not a problem, but this is condition 1. Even if you have some asymmetry during the collapse, at the end, it's much more spherical than a binary system. So it's much more difficult to detect. Okay, so in the particular case of a binary system, you can compute exactly, not just with ends, but exactly the power which is emitted. It depends on the total mass and the reduced mass of the system, and on the separation, or in an equivalent way, of course, via the Kepler law, on the orbital frequency. And then somehow you can consider that at the first order, your system evolves by losing energy with this power. And here I have assumed a circularized system, so it's easier, but otherwise you would add also to add a second equation for the loss of angular momentum. But for a circular system, it gives exactly the same result. And you can compute the evolution of the separation. So somehow the separation will decrease. And you can compute the merger time, which is a very important quantity for a binary system. This is the time needed from an initial separation to reach the merger. And here a very important result is the fact that it depends to the separation to the force power. So even with a not too broad dispersion of the initial separation, you predict a very broad range of merger time. So for instance, for a binary neutron star system, typically it can be as short as 50,000 years for an initial separation, which is a milli astronomical unit, but already with 2% of astronomical unit, you reach the Hubble time. So it's also a big challenge for the modeling of the population of such binaries that merge, because somehow you have to understand how it is possible to produce a binary system with such a short separation. And this is where, you know, the common envelope phase with some friction plays a major role to allow this low separation. So for a more massive object, you see that the evolution is faster due to the mass factor at the limit. So here is an example of the evolution of a binary system. So this is a famous binary pulsar of Olsen and Taylor. And you have both the evolution of the separation and the eccentricity. And one well-known effect of this process is also to circularize the orbit. That's why for isolated system, when you are interested only in the last orbit and the merger, you can always assume with a good precision that it's a circularized system. So this is not a good target for like and then the signal itself one important information is that the frequency of the signal is twice the orbital frequency of the system. So somehow when you measure your signal, you have already a direct information on the binary system. And the second interesting information, as I told you, is the fact that the amplitude decreases like 1/d. And then there is a modulation that is not written here with inclination. So this is one difficulty in the measurement of the distance. In practice, you have a degeneracy between distance and orientation of your binary system. So I will skip the equation, but an important result is the fact that you have an invariant quantity with the frequency of the signal and the time derivative of this frequency. If you produce this quantity, it's a constant, which depends only on a combination of masses, which is called the chirp mass. And so the chirp mass is a quantity which is quite directly measured when you detect gravitational waves. So it's a summary of these important quantities with order of magnitudes. So see the order of magnitude for the strain. Here I have normalized with typically a binary neutron star system. And then we can see how it can be used to infer very important physical information from the in-spiral phase. So when the two objects are still orbiting each other before the merger. So typically with the frequency evolution, you will measure the chirp mass. So this quantity. And once you have the chirp mass, where was it? Once you have the chirp mass, sorry, it was this slide, the amplitude of the signal depends only on the frequency that you know and the distance. So this is a unique case in astronomy where when you detect your signal, you have immediately the distance, which is quite impressive. Okay, so and then if you have a very accurate measurement, the detailed comparison of the predicted signal, so what is called the waveform with what you measure, so especially the evolution of the phase, allows to test higher order terms in the prediction. And then you can have a measurement of the individual masses, of the spins. And in the case of neutron star, you can even measure the way the two stars are affected by tidal forces in the very last orbits before the merger, which, for instance, is very interesting because it depends directly on the equation of state of a very high density matter. So it's something quite interesting. Another interesting thing, as I told you, the frequency of the signal is in fact twice the orbital frequency. So via the Kepler law, you can compute it. And then if you assume that your objects are black holes, the final separation when you have the merger is of the order of the radius of the last stable orbit around the black hole, which is proportional to the mass. So at the end, you get a frequency which goes like 1 over the mass. That's why when you go to millihertz, you move from stellar mass black holes to supermassive black holes, typically the low end part of the distribution of mass of supermassive black holes, 10 to 6, 10 to 7 solar masses. Okay. So then, if you are lucky, I mean, in most cases, this is the signal from this in-spiral phase, which is detected. But if you are lucky, you can also detect the signal during the merger. So for two black holes, the merger, it's mainly when you move from two separated horizons to a single horizon. For two neutron stars, it's much more complicated. It's really a complex interaction between the two objects. And then once the merger has occurred, somehow you will have a last signal because somehow the system has to relax. So again, when these are two black holes, it's quite simple. You have formed now a single black hole, but with a very complex horizon shape. So somehow it's a dynamical black hole, which has to relax towards the only steady state which is possible, which is the so-called Kerr black hole. And to do that, it emits gravitational waves. So in the case of two black holes, if you measure this so-called ring down emission, you can fully characterize the final black hole, whereas from the in-spiral, as I told you, you have characterized the initial two black holes. So again, it's a very unique case in astronomy, where a single observation gives you both the initial and the final state. And in the case of a neutron star, observing these two signals, which has not been done yet, would be of first interest because somehow the post-merger signal will tell us something like once the two neutron stars have merged, do you form immediately a black hole, or do you form an hypermassive neutron star which lives for a long time, or do you form a neutron star not very far from the maximum mass, and after some accretion it collapses to a black hole, etc. With the post-merger signal, you would have a direct information about that. And of course, for the merger itself, it's something for which we lack excellent prediction because it cannot be treated in somehow a well-defined system like here with a PPN calculation or here with just perturbation theory. Somehow here now you have to do a numerical simulation with the best physics you can, but it's never fully accurate. And so somehow probably if we detect that, we will learn more on our simulation and the way to better understand the physics and really make physical measurement, I guess. So if we take, for instance, the first detection, this binary black hole in 2015, direct application from this graph, which gives frequency as a function of time, you measure this invariant and you have the chirp mass. And then you move to the top panel, which gives you the signal as a function of time. And from the amplitude, you get the distance. So you see very well that we have typically 7 or 8 orbits with a frequency which is rising. So the peaks are closer and closer. Then the merger and the post-merger signal. As there are here 2 detectors, by triangulation, you can have an idea of the localization. Here we face the first difficulty. So it was somewhere in the southern hemisphere, but with a very, very large error region. So the precise modeling of this frequency evolution gives you the chirp mass. So we have 2 black holes of about 30 solar masses, and then combining with the amplitude, a distance of 400 megaparsec. And this is typically the kind of diagnostic which can be done for every detection because I mean, with an accuracy which can vary with the signal to noise ratio, but this is the information we always have. When we have also the ring down emission, like in this case, we can measure the physical properties of the final black hole. And of course, what is interesting is that in this case, you can evaluate how much energy has been released. And it's about a factor of 50 times larger than typically the energy released in a core collapse and emitted as neutrinos in a core collapse supernova. So it's really impressive. And here in this first detection, the result agrees very well with numerical relativity. And you can compute the peak luminosity in solar luminosities. And I made a rough estimate. So I took an universe which is homogeneous over the size of the Hubble distance with a number of density I deduced from the local density of galaxies. So it's probably not very accurate. All galaxies are Milky Ways with the same power. So it's again not very accurate. Because, but at the end, I guess I get that this single event is about 100 times brighter than the whole electromagnetic observable universe. It's just extremely difficult to detect. Okay, so we'll skip that. And so now, maybe, what time is it and how much time I have? 10 minutes. 10 minutes. So we'll skip backgrounds. It's in the near future, probably, we will detect gravitational wave background in the Hertz kilohertz range, and it will be very interesting. We can discuss that later if you want. So I will take the famous event to conclude and show all the diagnostic we can have with that, and conclude at the end that probably we won't have similar events soon, and that we have to be clever to get similar information. So as you know, when 2 neutron stars merge, you expect a lot of things. So the central region will collapse to a compact object. So either directly a black hole or with an intermediate state as a massive neutron star. So this is what I have plotted with this white circle for described reason. And then part of the material is immediately expelled. This is called the dynamical ejecta. And part of the material remains gravitationally bound to the central object and will form a disk around this black hole, let's say. So the dynamical ejecta is very interesting because it leads to one of the first electromagnetic counterpart you can expect, which is the so-called kilonova. So the idea is that it's a high velocity material, very dense and very neutron rich because it's inherited from the two neutron star. And so this is a place where you can have a very peculiar nuclear process called the rapid neutron capture, which will produce heavy elements which are radioactive. And then you have a very standard evolution where the ejecta evolves with heating due to the radioactive decay of your new formed elements and some cooling due to the expansion plus the radiation. And it was predicted before the first detection with typically an emission peaking in the visible and the infrared. And it's not too anisotropic, okay, let's say. And then as we have a black hole with a disk, we expect also a relativistic ejection. And in this case, it's highly anisotropic, because it's a jet, and in addition, because it is a relativistic jet. So dissipation in the jet was expected to produce short gamma ray bursts because we have many indirect evidence for the association of short gamma ray bursts with binary neutron star systems. And then the deceleration of the jet produces a multi-wavelength afterglow from X-ray to radios, and maybe even up to very high energy gamma rays. And again, this is difficult to detect because it's highly anisotropic. So, okay, we'll skip that. This is just to illustrate the formation of heavy elements. Yes, you see, you capture a lot of neutrons very rapidly, and then you decay slowly towards the valley of stability. Okay, and this is the decay which can hit your ejecta. Here, as you know, it started with the detection of a gamma ray burst, a short gamma ray burst, probably a 2-week to trigger a follow-up if it was just that. But very rapidly, it was understood that a few seconds before, a gravitational wave signal had been detected. Here it's a case where you can really see with your eye, especially here, the frequency evolution. And it's much slower than in the previous example. I don't know if you have noticed when I have shown the binary black hole, the total duration was extremely short, was about a few 0.1 seconds. Here we have tenths of seconds. It's much slower. It means that it's a less massive system, so a binary neutron star. And then here the localization was done both by triangulation between the detector and in addition by using that, as I told you, from the analysis, you have immediately an idea of the distance, and it was not detected in Virgo, but from the antenna pattern of Virgo, we know that at this distance, it could be detected in some direction. So you eliminate this region, and this is how you move from an error box of 200 square degrees to an error box of 30 square degrees, which is a big improvement. And now you just have to observe all the galaxies, but this is something you know much better than me. Here, the main problem, I think, was to wait for the night in Chile. So I guess that everyone was just looking at one's clock. And here are the winners. The kilonova was found. It's really, this map is impressive because you see you have somehow all the localization by independent methods. So not only the localization by gravitational waves, but also using the gamma ray burst with the interplanetary network. This is a ring, just with Fermi, this is this region. And then on top of that, exactly in the center, the kilonova. Okay, so you see the kilonova on the day of the discovery, and a few days later, it shows that another difficulty that you have really to go very fast, because 1 week later, it's already more or less too late. Somehow it's a case where it was the first detection of a kilonova, or a non-ambiguous kilonova, And somehow the evolution fits very well with the theoretical prediction, with one additional complication, but which was already discussed before the discovery, which is that probably in addition to this dynamical ejecta, which is immediately expelled during the merger, you have probably also a more polar ejecta, which is a little less neutron rich, and where you have a second contribution to the kilonova light. And one possible scenario for that is that you don't form immediately a black hole, but first a neutron star. And this neutron star emits a polar neutrino-driven wind along the polar axis, which leads to this second component. And the first component, the dynamical ejecta, peaks later in the red, and the second component, due to the polar ejecta, peaks earlier in the blue. And you not necessarily expect the blue component in all events. So in the future, when we will have a lot of kilonovae detected, it will be very interesting to have a very efficient follow-up to detect it very early, to be able to know which one has a blue component and which one do not have. And it will give some very important information about the post-merger evolution of the central source. Okay, once you have a kilonova, what is very nice is that you have now sub-arc second localization, so you can point towards this direction at all wavelengths. And so this is how an X-ray and later a radio source has been detected. And now this is the afterglow. So you see, we were extremely lucky because it was the first time that we had the gamma ray burst, the afterglow, the kilonova. And it has never happened again since this day. And probably we were extremely lucky. So we can imagine in the future to have combination of that, but everything in a single event. We'll have to be extremely lucky a second time. So what can we learn? And this is really where this is multi-messenger astrophysics, because I think the most important message is that each messenger is carrying a very complementary physical information on the astrophysical source. And when you have all the information, which means a very efficient follow-up, you can really deduce a lot of things. And here we have a single event, but it's still studied today because there is still a lot of information to extract. So from just gravitational waves, we know more or less all the properties of the initial binary system. There is even a constraint on the viewing angle. So we know that we see the system off axis. And there is, of course, some constraint on the deformability in the last star orbit. So we have an interesting constraint on the equation of state of the neutron star. Then, so this is that. Then, from the kilonova, we can do many things. First, somehow, we prove that these were neutron stars, because we know that there were plenty of neutrons. So it's a direct proof that we had neutron stars. It's quite interesting. We learn a lot about this post-merger evolution, the different ejectas, as I told you, the composition of these ejectas. So somehow we also prove more or less directly, depending to whom with whom you discuss, that the air process, the rapid process was at work in these ejecta, and that we have now identified clearly a potential astrophysical site for the heaviest element in the universe. And already, just to notice, it's very nice to see such a black body cooling over a 1 week scale. And then, if you combine already these two signals, as you have the distance with gravitational waves and you have the redshift with the host galaxy, you can measure the Hubble constant. And I thought it was my next slide, but no, it's not the case. Here it's just a comment to say that, as always, when studying transient events in astrophysics, the host galaxy itself carries also a lot of information. And so, for instance, here, this is a galaxy which is not really forming stars today. And it fits very well with this scenario where you usually expect quite a long delay between the formation of the binary system and the merger. And so somehow it's interesting because, again, if we have a sample of such events, we can learn something about, for instance, the distribution of merger time and so the properties of systems at birth. I have 1 minute to conclude. So About the short gamma ray burst, this is maybe where this first event was the most puzzling, because the short gamma ray burst is the closest short gamma ray burst ever detected, and it is also the weakest, which is strange. But the answer is we see the system off axis, and probably we don't see just a standard short gamma ray burst coming from the core ultra-relativistic jet seen off axis, but more something coming from a material around this core jet. And why do we know that there is this material? Because we need it to explain the afterglow. This is the next slide. And the idea is that the jet produced by the black hole, this system, had to go through the kilonova ejecta. And during this interaction, it has created some kind of cocoon or around the jet. And when this cocoon, when the jet emerges, you have a shock breakout emission, like in a supernova, but in different condition, and this produces a short gamma ray burst. If we had been aligned with the core jet, probably we would have seen a standard short gamma ray burst, but of course, we will never know, so it's very easy to say. And the presence here, it's very nice, because the fact that there is a relativistic jet has been directly confirmed by VLBI measurement, so there is a superluminal apparent motion. Of course, it will be difficult to have such observation in the future, except if, again, we have a very nearby event. And then the afterglow itself, it's very interesting, because it has shown first a rise for hundreds of days, and then a normal decay. And again, the interpretation is quite clear today. So the main axis of the ultra-relativistic core is like that, and you are in this direction. And this is surrounded by material which is only mildly relativistic, mildly energetic. So initially, everything is moving at the speed of light. So each part of this complex region is focusing radiation in one direction. And so you see only the small part coming in your direction, and it is not very energetic. But then due to the deceleration, the Lorentz factor decreases, so you are less and less bent, and you start to explore more central region. And you reach the peak when, for the first time, you detect the emission from the ultra-relativistic core jet. And then you recover a standard decay due to the deceleration. And so this is very interesting, because it was the first time we could detect the jet of a gamma ray burst off axis and learn all this geometry. And just the afterglow, to give another example, it gives a lot of information, not only on the jet, as I told you, but also on the environment. We can estimate the density. And here it's a case where we have a very nice data sample. So the synchrotron component of the emission from X-rays to radio is very well measured and very well fitted. And then it allows to predict what could have been the TeV emission, for instance, if some of you are interested in the follow-up with the Cherenkov telescope. And here the conclusion is that it was about 2 orders of magnitude, at least below the lower limit obtained by S at the peak. But using the same parameters, we can see that just being slightly less off axis, because of course, the off axis angle have a very strong impact due to the very high Lorentz factor, or being in an environment which is a little more dense, would have made the event observable probably up to 100 megaparsec with CTS. So still really worth to look for such event. And I will conclude by this slide. I think it's just the beginning. We have just to be patient, because it's really a big challenge on the instrumental observational side, and this is probably why such a workshop is organized. But really, the potential is extremely high on the point of view, not only on astrophysics, but also fundamental physics and cosmology. And I think that we have also to be clever and to exploit all the channels. Of course, the Graal is a single multi-messenger event, but it can be crossed with many other channels. And just to take the example of binary neutron stars, for instance, we can also observe, for instance, gamma ray burst plus kilonovae without gravitational wave. It has been done since 2017, so it's very interesting. And I think that in the future, we can also maybe hope with, for instance, a telescope like the Vera Rubin Observatory, try to search for orphan kilonovae or orphan afterglows. This is almost as difficult as detecting gravitational waves, but if we have only a few events with each channel, at the end, we have a very interesting sample with a very complementary information again. And I will stop here. Thank you very much.